Hello! In this video we are continuing our discussion of section 8.6 on representing functions as power series. In our second day of the lecture we're concentrating on coming up with new power series for functions by using differentiation and integration. So for example, here in example 2 we're going to consider the geometric series that we obtained in example 1 part A, so that was in our previous lecture for this section. So we have the function 1 over 1 minus 2x was equal to the sum from k equals 0 to infinity of 2 to the k x to the k. If we wrote out our terms, we would have 2 to the 0 times x to the 0, so that gives us 1, then 2 to the first times x to the first, so 2x, 2 squared, x squared, so that's 4x squared, and so on and so forth. And we had that our interval of convergence was x value strictly between -1/2 and 1/2, or we could write that as the absolute value of x is less than 1/2. And we have been asked to find a power series representation for the natural log of 1 minus 2x, and we need to answer the question, what is the radius of convergence for the new power series? So just like what we did in the example from the previous lecture where we used algebraic techniques to come up with new power series, we need to relate the two functions that we have been given. So we need to relate these two functions. So the question is, how are natural log of 1 minus 2x and 1 over 1 minus 2x related? Now with this relation, there are a few options that you have. You have the options that we talked about in the previous lecture, so those are the algebraic options. So that would be a sum or a difference. Those options aren't as common because it requires you to have two functions that you are adding together or subtracting, and that is definitely not the case here. So that's not the option that we want to use here. We also can multiply by a power of x. So that would mean we would take our 1 over 1 minus 2x and multiply by a power of x to get to the natural log of 1 minus 2x. That's definitely not the case here. We also have the composition or substitution. So this would be substitute in a function for x. So we would take the x here and substitute some other function for x in there. So 1 over 1 minus 2 times something, which is not what we have with the natural log. So it's not that option either. Now with what we have seen in this lecture, we also have integration or differentiation. So then the question is, can we differentiate 1 over 1 minus 2x to get to the natural log of 1 minus 2x, or can we integrate 1 over 1 minus 2x to get to the natural log of 1 minus 2x? And in this case, the correct option is integration. If we were to differentiate 1 over 1 minus 2x, we could write that as 1 minus 2x to the negative 1. If we differentiated this, it will give us a negative 1 minus 2x to the negative 2, or negative 1 over 1 minus 2x squared, which is definitely not what we have. Integration, however, is going to work. So let's notice that if we integrate 1 over 1 minus 2x dx, we're going to need to use a u substitution for 1 minus 2x. du is going to be negative 2 dx. So we have negative 1/2 du equals dx. So this is going to be a negative 1/2 integral of 1 over u du, and that's going to be negative 1/2 natural log absolute value of u plus c. So we'll get a negative 1/2 natural log absolute value of 1 minus 2x. And I know we're off by an absolute value here, but that part doesn't matter all of that much. So we will say that this is the function that we want here. Negative 1/2 natural log of 1 minus 2x. But we want a power series for just the natural log. So what we have is the integral of 1 over 1 minus 2x dx is equal to negative 1/2 natural log of 1 minus 2x. So we are going to multiply both sides by a negative 2 to get that the natural log of 1 minus 2x is equal to negative 2 integral of 1 over 1 minus 2x dx. Now the reason why we did that is, we have a power series for 1 over 1 minus 2x. We know how to integrate a power series. And we can multiply a power series by a constant. So that means then that we can come up with a power series representation for the natural log of 1 minus 2x. So then, continuing with what we have, natural log of 1 minus 2x is equal to negative 2 times the integral of this. So we're going to have negative 2 times the integral of the power series that we had. Let's see if I can remember correctly. The sum from k equals 0 to infinity of 2 to the k x to the k. And let me check that real quick. Yes. So we're going to integrate this with respect to x. We can integrate this term by term because that's how we integrate and differentiate power series. So it might be helpful if we actually write out our terms. So that was 1 plus 2x plus 4x squared plus 8x cubed plus so on and so forth. So we'll have negative 2 times, if we integrate a 1 dx, we're going to get an x. If we integrate a 2x dx, we're going to get an x squared. If we integrate a 4 x squared, we're going to get a 4x cubed over 3. If we integrate 8x cubed, we're going to get a, 2x to the 4th. Plus so on and so forth. But it'd be nice to have it written in closed form, which is this notation with the sigma and everything. In order to do that, we can actually, so we can do this one of two ways. We can look to see if we can find a pattern for these terms and then write it in terms of the closed notation, or we can go straight from the closed notation to here. So we have negative 2. We are integrating with respect to x, which means that everything except for the x is considered constants. This sum notation, the sigma notation, is just a succinct way of writing a sum, and we know that we can integrate term by term, so that means that we can actually pull the sum outside of the integral. So we integrate 2 to the k, x to the k dx. But 2 to the k is a constant because we're integrating with respect to x, which means that this is equal to negative 2 times the sum from k equals 0 to infinity of 2 to the k times the integral of x to the k dx. Now we have x raised to a constant, which means that when we integrate, we're going to add 1 to the power and divide by the new power. We still have our 2 to the k out here. We have our sum from k equals 0 to infinity, and we have a negative 2 there. Since we have a indefinite integral, we do need to remember to add c. Notice up here, when I was integrating the function, I dropped off the c because of the fact that we don't really need this right here, okay? Since we're integrating, sort of integrating both sides here, we really only need one arbitrary constant. So I'm going to go ahead and add it on here, all right? If you do term by term integration, then you would need to remember to add c out here And I just realized I had a notational mistake there with rewriting the dx. So we would have a plus c there. Okay, so going back to what we have, -2 sum from k equals 0 to infinity of 2 to the k x to the k plus 1 over k plus 1. If you want to, you can move the 2 inside and combine the powers of k so that you have 2 to the k plus 1. You do not have to do that though, so if we did, we'd have negative sum from k equals 0 to infinity of 2 to the k plus 1, x to the k plus 1, all over k plus 1, plus c, and we have, if we bring down our left side, the natural log of 1 minus 2x is equal to that. Notice, to obtain the value for c, the easiest thing to do is to plug in x equals 0. And the reason for that is if you plug in x equals 0 here, it's going to make the entire power series go to 0. So we have natural log of 1 minus 2 times 0 is equal to negative sum from k equals 0 to infinity of 2 to the k plus 1, 0 to the k plus 1, all over k plus 1, plus c. Notice if we take 0, we raise it to a bunch of powers, it's all going to be 0. We multiply by a constant, we divide by a constant, it's all going to be 0. We sum up a whole bunch of zeros. This whole thing ends up equaling 0. So that 2 times 0 also gives us 0. The natural log of 1 is also equal to 0, which means that we get that c is equal to 0. So then our function, natural log of 1 minus 2x is equal to, the power series is negative sum from k equals 0 to infinity of 2 to the k plus 1, x to the k plus 1, all over k plus 1. You can, of course, bring this negative sign in here as well if you'd like. You're just not going to raise it to any power. So that is our function and our power series representation. The problem also asks us to find the radius of convergence. Not the entire interval of convergence, just the radius of convergence. And that is a good bit easier here. For the radius of convergence, since we used integration to find the new power series, the radius of convergence stays the same. So originally, the interval of convergence was absolute value of x is less than 1/2. This means that the radius of convergence for the original power series is 1/2. So our new power series also has a radius of convergence of r equaling 1/2. Notice if we were asked to find the entire interval of convergence, we could find our most of our interval by looking at our center, which in this case is equal to 0, and we would add the radius and subtract the radius, which would mean that the interval of convergence, we would contain 0 plus 1/2 and 0 minus 1/2. Oops. So we get the interval between negative 1/2 and 1/2, but we must check the endpoints. So this would be just the same as if we were applying the ratio test. We would take x equals negative 1/2, plug it in, figure out if it converges or not, x equals positive 1/2, and so on and so forth. Okay, so with this theorem involving differentiation and integration of power series, we do have a radius of convergence that follows through if we integrate or differentiate to find a new power series. But if the problem asks to find the entire interval of convergence, then you can at least work with the center for your series, and you can figure that out just by looking at the series here. If we set that equal to 0, we end up getting that x equals 0, so this is our center. So we pick our center, or we find our center. Our radius comes from the original power series. We add the radius, subtract the radius to get most of our interval, but then we do have to check the endpoints. And you will see this in more detail with the next example in this lecture.